Hello, my name is Jim Carr, and I'm the StereoBit project principal investigator. StereoBit is an application for the SpaceCube processor. We intend for this presentation to be informative for those who may be considering developing their own applications for the SpaceCube family. We also hope that you might find the StereoBit application interesting from a science perspective, and we certainly hope to fly it in a not too distant future. Our work has been supported by AIST under the Advanced Information Systems Technology program. I will provide a brief introduction to SpaceCube and the StereoBit science application. Then I will describe our recommended development workflow for SpaceCube applications that we successfully use for StereoBit. It is quite applicable to a broad range of mission applications. After this introduction, Joseph Westra will walk you through the high-level synthesis process and demonstrate building and testing StereoBit. We hope that you will consider SpaceCube for your mission applications and find this video useful. The SpaceCube processor family, developed at Goddard Space Flight Center under AIST sponsorship, bridges a gap between computing on terrestrial computers and radiation-hard space processors. SpaceCube offers a radiation-tolerant platform for supercomputing in space, delivering a remarkably high ratio of compute power per watt of consumed electricity. The SpaceCube family does this with a novel reconfigurable computing architecture that uses field-programmable gate arrays, or FPGAs, that can be used to perform computations. The SpaceCube Minis are the third generation of the SpaceCube family, with form factor and electrical power requirements suitable for CubeSats. Many classes of problems, such as those in AI and computer vision, lend themselves well to calculation on the FPGA fabric, where the full potential of the SpaceCube family can be realized. Control flows that do not readily parallelize can be executed on a CPU, either the Mini-Z ARM or a Microblaze soft core on the FPGA fabric. The non-traditional SpaceCube architecture makes developing for the SpaceCube family different than that for conventional processors. Many of the development tools that are taken for granted by scientists and software engineers are in a less developed state for computing on an FPGA device. One of the primary purposes for our project is to advance development capabilities on these devices. We do this by working a specific science case tied to high-priority decadal survey science from conception to near flight-ready status, and sharing best practices and lessons learned about developing for these devices with you, the community. Next, I will describe our science case and explain why SpaceCube's computational power is essential to enable a new observing strategy solution for these observations within a constellation architecture. StereoBit exemplifies a new observing strategy leveraging multi-platform distributed observing, onboard intelligence, and hardware miniaturization to deliver high-priority decadal survey science. In this case, resolution winds in 3 dimensions within the atmosphere, from the planetary boundary layer to the tropopause. StereoBit observes clouds in motion coordinated between platforms and applies structure for motion methods to measure parallax and displacement in time with subpixel precision and thereby resolve wind coordinates in 3 dimensions within the atmosphere. A StereoBit observing constellation, illustrated to the left, can fuse observations from low Earth orbital or LEO satellites and operational geostationary satellites, as well as tandem observations by pairs of LEOs. Individual LEOs each produce 3 continuous strips of imagery looking forward, nadir, and aft. A challenge with high-resolution multi-angle observing at a global scale is the sheer volume of science data. Traditional observing approaches would collect all science data and process it on the ground in a centralized facility to create the science product. We employ a different strategy: disaggregation of the science data processing to perform science processing on board and thereby reduce the volume of data needed to be downlinked to the ground without sacrificing science quality or limiting the geographical extent of science observations. Our science algorithms derive from stereo winds work fusing data from NASA's MISR instrument and NOAA's GOES weather satellites. An example product created from MISR and GOES is shown at the right, where the color coding represents the wind height and the vectors scale in proportion to the wind speed. Our targeted sensor is the ESTO-funded CMIS from the Instrument Incubator Program. CMIS has 3 spectral channels, one with stereo capability at 3.75 microns wavelength. It is compact and power efficient thanks to an advanced high operating temperature or hot detector technology and can be accommodated on a CubeSat. CMIS recently completed an air campaign consisting of 1 engineering and 3 science flights. The false color composite on the right collocates CMIS pixels from its aft, nadir, and forward-looking 3.75 micron channel. The different looks are acquired at different times when CMIS is at different positions on its flight line. The color separation is the disparity that indicates either motion or height. Static and low objects appear in grayscale. A paper for the journal Remote Sensing is available in preprint that describes CMIS and these results from an air test campaign. Excellent comparisons were found between CMIS stereo heights and Calypso and Aeolus LiDAR datasets, as well as with digital terrain data showing about 20-meter height retrieval accuracy from the air. This scales to 100 to 200 meter wind height resolution from space, which is extremely good. The processing of these aircraft datasets used our StereoBit C language prototype code. The StereoBit SpaceCube application is the level 1 processing for the Stereo 3D Wind science application just described. It is computationally intensive and implemented on board to fulfill a new observing strategy approach for a Stereo 3D Winds constellation. The upper block diagram shows the functional components of StereoBit comprising context image compression, structure from motion, disparity calculations that are the basis for extracting wind tracer heights and wind motion, and pixel geolocation. When developing StereoBit, we fly it in an application development testbed in a lab at Goddard Space Flight Center. This allows us to test with CMIS proxy data that we derive from MISR datasets and flow data end-to-end in a flight-like manner to create science products such as that shown at the right. An application development testbed, as shown below, can include virtual components to represent other nodes in the system, both in space and on the ground. The Virtual Constellation Engine is a good tool for this purpose. It allows emulation of other nodes in the cloud to facilitate hardware-in-the-loop systems testing. Our project also upgraded the VCE to include the capability to model global networks such as Starlink and implement communications policies to manage contention for ground station resources. Our best practice recommendations for SpaceCube development workflow begins with developing a mature and well-tested science prototype. This is familiar work for most scientists and software engineers. Proxy data sets for testing are highly important in these steps, and the proxy data should be used again in later testing on development boards and in-flight hardware testbeds. High-level synthesis, or HLS, is the key technology that makes development of complicated science applications even remotely feasible on FPGA devices. HLS translates a high-level language such as C or Python into a hardware description language for the FPGA fabric. This will generally include soft cores to run control flows and linear calculations that interact with accelerated computational functions synthesized into the FPGA fabric, with parallelization and pipelining where applicable. StereoBit used the Xilinx Vitis tool to synthesize the hardware definition from a C language prototype. This is analogous to using a compiler and makes development much more efficient in terms of labor hours in comparison to coding using a conventional hardware description language, or HDL. Coding directly in HDL would be akin to writing a complicated program in assembly language. The final step in the development process includes packaging as a core flight system, or CFS application, to run over the PETA Linux operating system. This enables easy deployment onto the flight hardware and facilitates operations with a command and control system such as Ball's Cosmos. Python is also available as a prototyping language that can be synthesized for the FPGA following the hot and spicy flow developed by USC. Our team has recently integrated the new Xilinx Vitis HLS tool into hot and spicy. Testing on development hardware lets one verify that the application fits within the necessary resource limits. Here are some results from StereoBit using the Xilinx KCU105. The KCU105 has a smaller FPGA fabric than the SpaceCube Mini that we are targeting. So if the KCU105 board will support the application, it will definitely run on the SpaceCube Mini. There are three important resources to verify. First is available fabric. Fabric utilization is measured in terms of lookup table connections, flip-flops, block random access memory, and digital signal processing cores. We show at the left the SpaceCube fabric utilization as the sensor cross-track pixel count varies. There are no gold rules for fabric utilization, but it's generally a good idea to leave some margin. Otherwise, routing on FPGA can become problematic, resulting in timing issues. Next is margin against real time, as the application must keep up with the flow of input data. In the middle, we show execution time as StereoBit running as fast as it can. It needs to execute faster than the purple line. For comparison, we have the StereoBit pipeline C language prototype running on laptop and server hardware. In general, you should not be surprised that the high-level synthesized version runs a bit slower on the FPGA device. This is because the terrestrial computer's very high clock speed. However, keep in mind that these terrestrial computers are not radiation tolerant, are much larger in size, and consume much more power. Basically, it would be difficult to fly them on a CubeSat. Power is the third resource to verify. High-level synthesis provides an estimate of the power consumed when the application runs. This is shown for StereoBit on the right. We measure the actual power consumption by StereoBit, and it's about a watt larger than estimated in some cases. However, this includes some overhead from the evaluation board. I'm done with our introduction to SpaceCube and StereoBit. Now Joseph Westrow will demonstrate the high-level synthesis workflow for building SpaceCube software using StereoBit on the KCU105 as an example. Feel free to email any of us if you have questions about either SpaceCube or StereoBit.
Here's an overview of the high-level synthesis workflow for app development on SpaceCube. First, make a prototype for your science algorithms in C++. This will provide a framework for the structure of your HLS code and will serve as a baseline to compare HLS results to. Here you can take full advantage of C++ constructs like dynamically allocated data structures, because this code will not be run on the FPGA. Next, rewrite your algorithms in Vitis HLS, being conscious of FPGA resources and HLS compatibility. Constructs such as system calls, dynamic memory allocation, and recursive functions are not synthesizable. Also, consider using HLS streams in place of large arrays to minimize storage footprint. You can add special macros, called pragmas, into your code to improve efficiency. Some use cases include pipelining loops, partitioning arrays, and inlining functions. When you are finished programming, open the project settings and specify your top-level function, the equivalent of the main function in standard C++. Ours is called StereoBit. Then run C synthesis. This will compile your C++ HLS code into Vivado-compatible RTA. After compilation, you can examine the resource footprint of your design and the generated report. Finally, export the RTL for your design as a zip file and open Vivado. In Vivado, open the IP catalog and import the HLS IP you just generated into your user repository. Then open the IP integrator to add the IP into your block design, along with any other necessary components. Once you have completed your block design, generate the bitstream, which you will use as the hardware basis for the Petalinux and bare metal apps. Once bitstream generation is completed, export it as an XSA file for importation into Vitis software and Petalinux. In Vitis IDE, create a new platform project and name it after your board. Then click Browse and import the XSA file you generated from Vivado. Make sure the operating system is set to standalone, and click Finish to create the platform project. Note that Vitis automatically extracts the bit and MMI files from the XSA. You may also need to code device drivers in C to allow your computer to interact with the board. In our test bed for StereoBit, we write binary files directly to the board's memory for StereoBit to process, so we need the drivers to define addresses. Next, create a new application project. Select the platform as the one you just generated. After you've named your project, you can use the Hello World template as a starting point for your program, as it automatically generates a main function and basic platform handling code. Once you have finished programming your app, right-click on the system application and build it. Now plug in both the JTAG and the UART cable into your board, and switch on the power. Open a serial port console window. You can do this in Vitis or another program of your choosing. In Vitis, right-click the debug option for your application and run your program. If you chose the correct serial port, you should see your program running on the board in the console window. You can use Windows Device Manager to find the serial port number for the UART cable. To run StereoBit as a CFS app on Petalinux, first create a Petalinux project using the Petalinux create command, specifying the path to the BSP for your board. Now enter the project directory. Now use the Petalinux config command to choose a hardware platform for your project. This will be the XSA file you exported from Vivado. Next, you can add user layers to and implement apps for your project. User layers go in the project spec folder. MetaUser is the default user layer, and MetaNASA is a custom one. Apps go in the MetaUser/recipes apps folder. This is where you will program your onboard Linux apps. For the most part, they will be the same as your bare metal apps, but you can now use the Linux file system for file I/O and control of peripherals. Back in your project root folder, you will need to enable your user layers in the Yocto settings of Petalinux config. To enable your apps, use the flag -c rootfs to open the root file system configuration and navigate to the apps menu. You can also use the rootfs config to enable a number of file system packages and utilities. To build your Petalinux boot image, run the Petalinux build command. On your first run of this command, this can take up to an hour, but subsequent builds will be faster, as Petalinux caches build files. To boot the image on your board, again open a serial port console window. Back in your terminal, run the Petalinux boot command with the JTAG flag. Depending on your development environment, you may need to open Xilinx hardware server and boot via its URL. In your serial port console, you will see the boot sequence for your Petalinux image followed by the execution of your app if you configured it to run on startup in your .bash RC. This concludes our overview of HLS development for SpaceCube. Because there are many steps for this process, we have included makefiles and TCL scripts to streamline the building and testing process, utilizing the command line capabilities of the Xilinx software suite. You can find more information on running the StereoBit testbed in our GitHub repository.